Bu arada Cem de burada master öğrencimiz Sezgin. Sezgin de Sabancı'da. Ee,
Memnun oldum.
evet. Sezgin'e ben bizim vektörü gönderdim. Onlarla bir CRISPR deneyi yapıp bir tane geni susturmaya çalışacaklar. Arabidopsis de yapmaya karar verdiler. Aslında başta başka bir fikir vardı. Ondan sonra işte selection kısmını o da yapacağı için ikinize birden anlatacağım. Hala kafamda böyle kompleks görüyorum. O yüzden hani çok böyle hemhal olmadığım için deneyle karışık anlatabilirim. Öyle bir durumda siz hani anlamadığınızı söyleyin ki müdahale edelim hemen. Okay, so now we'll see how we do the selection for CRISPR mutants. There are some tricks. I'll tell you these tricks from the presentation of Jan, a Russian student in the US. Yes. So, you know, our aim is to get mutations in CRISPR. Let's consider we only want to have one mutation. In arabidopsis, it's not so easy to get mutation from the CRISPR technique because the technique is not so efficient. So you need to maybe wait 2-3 generations to get one mutation. In the worst case, let's say, I mean, you can get it in just one generation. It's also possibility, but let's assume we get it later, because then the things get a bit more complicated, and this is what I want to share with you. Okay, so these 3 steps are important. I already, for Gem at least, I already created the Cas19 and guide RNA. Sezgin, you haven't have this guide RNA in the vector yet, right? Or did you do this? You did it.
Not yet.
Not yet. Yeah, okay. Now I remember. So I need to give you some hints also how to generate the guide RNA. There are a lot of techniques, tips, tricks. Okay, but we did it. And then the second step, we need to transform arabidopsis with Cas9 vector, which means the vector hopefully enters into the genome of the plant, but not in both of the chromosomes, just one chromosome. Usually it enters just one chromosome, not both of them. Okay, then how do we know if the vector is inside? Vector has a gene which gives resistance to the plant against an antibiotic. And then we sow the plants in medium containing antibiotic. The plants which can survive have the vector. So this was one essential step in CRISPR, doing CRISPR mutants. The second essential step is to select the mutants of interest. How do we select the mutants? So we already know they have vectors, but we also know having vector inside doesn't guarantee that you have the mutation. So we need to investigate in every step if there is mutation or if we should wait more, which means reproduce plants several times maybe. How do we do the screening for the mutation we want? When we design the guide RNA, we consider one region. So we want to mutate one gene on a particular region. So in guide RNA, I think we put 20 nucleotides or so, and we know exactly where it should make the mutation. Okay, so now I give you a tip. In our case, so with GEM, and if we design the vectors, it will be the same for Sezgin. What we do to make the process easier, we look for specific special regions to generate the mutation. Normally, we can generate the mutation in any place on the gene that we want to mutate. But to make the selection process easier, we can select regions on the gene which are already cuttable by the restriction enzymes. And the logic is that if there is a mutation from the CRISPR vector, then the restriction enzyme will not be able to recognize this region. And how do we do the selection? We will do PCR. We will get a band from the mutants and from the wild types as well. And then we will use the restriction enzyme digestion. The ones which cannot be cut are very good candidates for the ones that have mutation. Oh shit, I forgot to record. No, I'm recording it. Okay, good. Yes. Do you have any questions about this? Is it clear for you?
Clear.
Yeah.
Mm-hmm. Okay. So, Sezgin, you should also do this. Then it's easier. What if you don't do this? You'll have PCR products. Some of them belongs to mutant alleles. Some of them may be wild type alleles. The only way then to understand where the mutation is to sequence this band. So it's also a very frequently used technique. And if you have a lot of money and time, let's say, it's maybe more efficient than the technique we use. But I think we don't need to spend so much money on sequencing every product. Okay.
Hocam, now
Yes.
we have a BSA1 restriction enzyme, right? So you use that one, right?
No. That's completely different.
I see.
So yeah, but good. So I can give more details. Let's say we want to delete a gene A. Okay.
Okay.
We look for the exons. There is a software. This software tells you. I mean, we put the CDS sequence of the so coding sequence of the gene on the software, and the software tells you, "Oh, look, there are restriction enzyme cut sites here, here, and this gene, this enzyme. Okay, it gives you a lot of options.
Okay.
So this is how you select which region you want to cut, and according to your selection, you will design your guide RNA. Okay.
Okay.
For
Nice.
Utku's case, we already have these sites, restriction sites, and we should order the restriction enzymes. After PCR, Utku will try to cut the PCR products, and hopefully he will not be able to cut some of them, which will indicate mutations.
Hocam,
Yes.
for the software, is it good to put the cDNA sequence or completely gene sequence?
So they made it so nice, unbelievable nice. You just put the name of the gene, and the program does everything. The program is called chop, like chopping. Okay. Now I give you another detail. There is another possibility to make the selection even easier, even without using restriction enzyme cut sites. And in our case, we also did it. You can also do it, but it doesn't work every time. So the method for this is, instead of making the mutation only one side of the gene, we make the mutation two different sites for each gene. So we have guide RNA targeting the same gene on two different places. And these two regions have a length like 300 base pair or shorter. The literature says if you attack the gene from two different regions, there is a possibility that a deletion mutation can occur. Long piece deletion. I now forgot the official name for it. So a region will be deleted instead of just one nucleotide or two nucleotides. Like 300 base pairs will just leave the place. Okay, it's also possible, and then the genome will bind again together. So if it is the case, then when we do the PCR, even without doing the restriction enzyme digestion, we should be able to see bands every time the same length, but sometimes very shorter, 300 bases shorter. This will show us the mutant. So if we have a shorter band, we will have the mutant. But it's also a possibility that we will never have the short bands. We will only end up with long bands. And it doesn't mean there is no mutation. Maybe these same size bands have mutations inside. And the only way to determine it then is to use restriction enzyme digestion. Okay. Any questions about it? Good. Okay, so I told you about the screening for the mutants. There is another problem. Let's assume we have the mutant. Now we may have still a problem. Our task job isn't finished when we get the mutant, because the mutants may still have the CRISPR vector and it's not wanted. Because if there is still CRISPR vector inside, okay, the specific cut site is not there, so he cannot cut our gene again, but it may cut some other genes due to low specificity. So the golden standard to generate CRISPR mutants is to get rid of the vector. Then the problem arises: how can we get rid of the vector? Okay. Then this is one of the difficult things to understand. We need to always work with the heterozygous mutants until we get the mutation. Once we have the mutant plant that we want, and we make sure it's heterozygous for the CRISPR vector, we just now select its offsprings, the ones that doesn't have the vector. How do we know the ones that doesn't have the vector? Now, if you put them under antibiotic stress, now instead of selecting the green ones, you will go for the yellow ones, and you should rescue it before it dies. So this is the last step. Okay.
Yes.
Is it clear? So now we know what to do in the last step. But what to do? What are we doing in the intermediate steps? So we need to have heterozygous plants. We don't want the homozygous ones. We don't want the ones that don't have the vector. Now I can refer to the presentation again. Okay, so in the presentation, I'll also deliver it to you. We have T1 generation, T2 generation. So what do they mean? T1 means the transformed plants. So we do the floral dipping. So we dip the flowers of the plant to the bacterial solution. And then this is T1 generation. And when we get the seeds from these, which are T2 generation, we don't know how many seeds get the vector. And the way to select for it is putting this on antibiotic. I already did it for jam. So we already did this step. And we will now select only the green ones. Yes.
But the seeds which do not have any vectors will die on antibiotic plates,
yes.
right?
Yes, that's true.
But how do we select these plants?
We want the homozygous ones that do not have the vector on the very last step.
Okay.
Yes. Now I'm telling you about the intermediate steps. So these are two different processes.
I see.
Yes. So now we go for the green ones. Now the complicated part is coming. If you're ready. So we cannot directly select all the green plants. The reason is maybe some of them are homozygous for the CRISPR vector. And we don't want these. And we don't know which ones are homozygous. And we cannot detect a homozygous CRISPR mutant by antibiotic selection or by PCR. Because if you do PCR, doesn't matter if you have the gene on the allele on one chromosome or both, you will still have the same result. I mean, the band will not be much thicker or anything. So we need another method to differentiate the homozygous ones from heterozygous ones because we want to go with heterozygous ones. Can you follow until now? Jem, what do you think?
Yes, I can follow up, but I have some questions for later.
For later, okay. Yeah. Okay, now the presentation tells us there might be two different procedures. We can, but anyway, in both procedures, we need to, before selecting these mutants, you see my cursor, right? So we want to make sure the heterozygous ones, but the only way to make sure they are heterozygous is to get seeds from them and sow the seeds in antibiotic containing medium. Now I'll tell you how. So this is again the T1 generation. And from T1 generation, we do this antibiotic media. And now we have yellow plants. We don't select them. And now we want to know which ones we select out of the green ones. And for this, we get seeds from this one, this one, this one, this one. Okay, and then we sow these seeds. But to get seeds from this, we need to take them from the antibiotic medium to the MS medium first. Okay, we get them to the MS medium. Okay, and here you can see there is no yellow plant, which means the T1 plants didn't take the vector. So Sezgin, you may end up with these plants. But we already have the vector, we know. Okay, so we have the T2 seeds, we will sow them and we will take the green seeds to MS media, otherwise they will die, okay? Okay, then we can do the PCR thing, but I'll first tell this thing. Okay, so again, we have T2 seeds and we want to know which ones are heterozygous. We get seeds from each of them. Here you can see the T2 seedlings. We get plants and we get the seeds. out of them, and then we sow them, and then we see if some of them, if a plant has always yellow, it means it doesn't have the vector anymore. If it always has green, it means it's homozygous. This plant is homozygous for the vector. And if there are some yellow and some green, then it means these mother plants are heterozygous for the vector, which means they are our candidates that we should take. You got it, right? I mean, you select for heterozygous in T2 by looking at T3. Is it clear? So if so, I'll go to the last step, last trick, let's say.
Can you back to previous slides?
Yes.
Hocam, these T2 on MS media, these are the heterozygous, right?
No. So they are the ones coming from antibiotic stress. So we immediately put the seeds from T1. After dipping, we put the seeds into antibiotic. And from these, we take the green ones, which is a mixture of homozygous and heterozygous ones.
Yes.
And we grow them until they give seeds. And from these seeds, we put the seeds in an antibiotic medium and look for heterozygous ones and go back to the plant. Because now we have a lot of seeds from these plants, and we know some of them are heterozygous. After learning which are heterozygous, then we continue with these heterozygous ones.
Okay.
Okay. The last thing I'm gonna tell you is when are we going to do the PCR for selecting the mutants? I mean, we go for the heterozygous ones until we get the mutant. But we need to investigate if the heterozygous ones have the mutation or not. So if you look at this slide, just a second. If you look at this slide, you will see
Hocam ses gitti.
Can you hear me?
Yes.
Can you hear me?
Yes.
Yes, but okay. Continue recording. Okay, so you see the guy made a tick on 3 of the petri dishes, but not 2 of them. The reason for this is he did PCR and looked for the mutation, and then he saw mutations in these and these and these ones, but not in those ones. And that's why he put
that means, Hocam, you did PCR, but
so he did PCR and then he did sequencing.
I see.
He did sequencing. According to the sequencing result, this is the guide RNA, and here is the mutation. So there is one A, additional A. You see, this is the sequencing result. This was the expected result. So there is one E, A. And these three have different mutations. It doesn't have to be the same mutation. In fact, most of the time, you always end up with different mutations because it's a random process. Okay, so I told you to continue with the heterozygous ones, I think the time we look for heterozygous ones is we do PCR on these T2, one of the T2s, I think, and look if the mutant, if the plant has mutation or not. If the plant has mutation, and if we are now, it might be a bit complicated. So if you are looking for deleting only one gene, and if in T2 you find this gene, now you should go for homozygous ones. But if you want to delete more than one gene, then what you should do is to delete. You should go for the mutant one, but for the heterozygous ones, and then you should continue with the heterozygous ones and look for until you get the mutation in the other gene as well. Once you have the mutation on one gene, our task for this gene is completed. Guide RNAs worked very well. Yeah. And I should tell you, once you have a mutation, it's not like vector. It is on both of the chromosomes. So you don't have to worry, mutation is only one chromosome and not the other. I think it's in both of the chromosomes. Otherwise, you would know this in PCR, I think. Okay, how complicated it is?
Question.
Yes, please.
If you want a mutation on both chromosomes, why are we looking for homozygous mutants?
We are looking for. Yeah, you're right. I mean,
heterozygous.
If we are heterozygous, yeah, if we want to knock out more than one gene, then we cannot go for homozygous ones, because if we get the homozygous one, homozygous means has the vector in both of the chromosomes. Then when we knock out the other gene, there will still be the vector inside, and there will be no other means to get rid of the CRISPR vector. So for each gene you want to knock out, there will be one CRISPR vector associated, which can be carried either on one chromosome or both of the chromosomes. And if you want to delete two genes, this means until you delete both of them, you need to go for heterozygous ones. Because in the last step, you will select the plants that do not have any vectors. So wild type, I don't know, you cannot call it wild type, but I mean, the ones that do not have vector in both of the chromosomes. Homozygous also, they are also homozygous for, they can be called like this.
Hocam, bir şey sorayım. May I ask
Yes.
a question?
Please.
In that slide, we eliminate the second plant, right? Because homozygous for the vectors.
We eliminate second what?
Second plant here in that slide.
T2, you mean?
Red cross. Red cross.
Red cross. Red tick, you mean?
No, red cross and the upper one, the second one, second plant. In
Second.
T2 generation.
Yeah, okay. Yeah, they crossed it. By the way, you can use the annotation tool to show what you mean, but I understand right now. They crossed it because when they put the seeds, they saw
Homozygous?
Yeah, this is
Yeah.
wrong. This is wrong. So these all should be yellow.
Right.
Yes. No, in fact, it's not completely wrong. There is also a possibility that the vector enters in both of the chromosomes. Okay. If it is the case, then you'll always have green plants.
Mhm.
Okay.
This is homozygous case, right, hocam? For the vectors.
For the vector, yes. This is homozygous case for the vector. After floral dipping, it's there is a slight possibility you end up with vector on both of the chromosomes.
Hocam, for the second plate on T2 generation, you wrote they all had to be yellow. If they were all yellow, wasn't that mean our transformation was not
Didn't work.
successful?
Yes,
Yeah.
yes.
Okay, so again, it will be crossed, right?
Yes. That's true. Mm-hmm. Okay. So the guy used different methods for selection, which are very difficult. So when I was there, he was working on this for the last 3 years. A lot of work. Our work will be, I mean, with Jem will be very long also. So he'll just do some part of it. But we never know. Maybe it becomes very fast. I mean, we don't know. But anyway, it won't be. He doesn't need to put a lot of effort. I mean, as much as this guy, because he used different method called decaps. He synthesized primers a lot of times. There are other methods, as you can see. Okay, here on this slide you can see different types of mutations, but he only targeted one region. Okay, so he saw, for example, deletion. In some of the lines, he found one big deletion, 22 nucleotide sequence, 22 nucleotides, and so on and so forth for different genes. So you can end up with different mutations. Any questions? If not, I'll stop here. Okay, I'll put this video to a place where you can also reach, and I'll send you this presentation from Jan. Have a good day. See you later. Bye-bye.
Thank you.
Bye.
See you.
Meeting.